Okay, I'll go ahead and begin. I'm Daniel Johnson. I'll be doing this masterclass for today. This is my first masterclass with TriplePoint. I have been with TriplePoint since the end of July, and I'm the lead process engineer. Previously, I've worked for 15 years in the wastewater industry. Prior to that, in academia. I'm also a licensed operator in the state of Illinois. So today what we're going to be talking about is going through data, how we interpret our data, and how do we turn around and then use that data to diagnose and troubleshoot problems that we are having with our lagoons. So we're going to talk a little bit about lagoon process today. We're going to talk about biosolids and the impact biosolids can have on our effluent hydraulic principles in lagoons. We'll talk about nutrients and nutrient management in lagoon, since a lot of lagoons are now getting nutrient permits. We'll talk a little bit about algae and duckweed, not too in depth, but mostly how algae and duckweed can affect our effluent quality and maybe how we can maybe remediate that a little bit. And then we're really going to dive deep into data analysis, troubleshooting, and looking at all of the data, not as simply just trying to meet our permit, but how can we utilize that data to operate our wastewater treatment facilities. So, data only has value when we can use it to answer some questions. So yeah, we need to collect that effluent data. We need to put that in our DMRs. We need to submit that and make sure that we're not in violation of our permits. But we also need to use that data as a tool to run our wastewater plant better. So when we start to design our sampling, we can use that sampling plan to help diagnose problems and different performance issues as they arise, and then not try to scramble and figure out how to sample to figure out a problem later on. So things that matter when we start to talk about numbers, we look at lagoon performance. Lagoon performance is sort of a continuum, right? Because lagoons have very long retention times in many cases. So sometimes what we're seeing in our effluent today could be something that originated in an issue that was from 1 to 6 months ago in the past. It's going to differ across seasons. We know that temperatures have a major effect on our lagoon performance, precipitation, rain events. We know if we're in a northern climate, we might have lagoon turnover if those lagoons are not well mixed, so we can see turnovers just like you see in a normal pond or lake. And then other operating conditions that might affect. So do we have intermittent dumping? For example, do we receive septage? Do we receive leachate? Do we have industrial clients? Things along those lines that can affect our lagoon performance. We need to be able to look at those lab results and interpret those lab results and say, in the context of what I see from day to day, from flow, temperature, visual conditions, how does that really relate back to what I'm seeing in terms of my sampling regime and my results that I get from my day-to-day samples? So in this particular webinar, the goal here is not simply just compliance, but we're actually trying to use this data to understand how our lagoons work and how to improve the functionality of our lagoons over time. So let's look at reading our permit. We're going to talk about our lagoon effluent. That's pretty basic. What's BOD? What's CBOD? What's TSS? What's VSS? Why do we care what those things are, frankly? And we're going to talk about some of the ratios that we can use between TSS and BOD5 to actually sort of do a quick diagnosis to see if we can kind of point ourselves in the right direction. We'll talk about effluent ammonia, why your effluent ammonia might be high. Why do we care about alkalinity, and how does alkalinity affect our ammonia? We'll talk about total nitrogen. What happens if total nitrogen is high? This is a big one. We're just now starting to see we're starting to see lagoons that are getting total nitrogen permits. And so we'll talk about how we can actually treat total nitrogen in a lagoon and why that's important. And then an ammonia nitrogen diagnostic, so we can look at some of those ratios. So when we start to look at your permit, there's a lot of different things that we'll see on these permits. For example, we'll see daily maximums. We'll see weekly averages, monthly averages. We all know about those. And sometimes we get a daily violation. And so then we'll come back and we'll do another set of sampling that week so we can bring down our weekly average. So do we need to do that? When should we be sampling? Should I sample when it's storming? Should I sample, after there's a big event in our town, things along those lines? How frequently should I sample? What type of sample should I get? From throughout the 24-hour period a day, is the water coming into my wastewater treatment plant exactly the same? Should I be doing a composite sample or should I be doing a grab sample? How should I do those samples as well? What's in those samples? And what time of year are we sampling in? So, some samples will be, or some of the permit limits that we have or sampling regimes might change from season to season. Constituents like oil and grease, how do those affect? Do we have metals that are in our permit? Some do, some don't, depends on what state you're in. So when you start to read that permit and you look at the actual constituents in here, one of the big things that you'll see automatically on your permits is 85% minimum removal. And sometimes this is a little bit hard because from day to day, you might have a sample that comes in and it might be a very low influent level. And then based on your effluent from the same day, you might have a low effluent, but it might not comply with the 85%. But that's very strange because that influence from today, but that effluence from 3 months ago. So that can be tricky from time to time just to keep up with. So one of the things that we're going to talk about today, and I kind of break this down when we start to talk about wastewater treatment in general, but also with Lagoon specifically. For me, whenever I start to talk about effluent lagoon quality, we need to look at multiple different things. What's the influent coming into the lagoon? Because that's going to have a direct impact on our effluent. What's the lagoon infrastructure look like? Is the infrastructure in good shape? Meaning, do we have 6 feet deep lagoons that have 5 feet of sludge in them? Do I have trees and shrubs and bushes growing out of my berms? Are my berms eroding? Are they falling into the lagoon? What's my liner look like? Do I have punctured liners? Things along those lines. The biological aspects. What are the bugs doing? What's affecting my bugs? Do I have a good VSS in my water column? Do I have nitrifiers? Do I have heterotrophs? Are they happy? Do I have enough aeration? Hydrological. So when I start to talk about hydrological, I'm really talking about flow. What's my hydraulic retention time in that lagoon? Is it long enough? What's my mixing look like? Do I have a stratification? So is the top part of my pond really warm and the bottom part of my pond really cold and I'm not actually getting vertical mixing? In that case, I might only be using half of my volume if it's actually stratified. Also short circuiting. Is the water coming in the pipe and shooting straight across the lagoon? And in that lagoon where I was supposed to get 30 days hydraulic retention time, am I only really getting, maybe 2 or 3 days retention time? And then lastly, the people. All of these things relate back to the people and the operators and what we're doing there day to day. Do we have enough time allocated to the day to actually take care of our lagoon? And what are we doing out there at that lagoon to keep up with everything and to make sure everything is in a really good state so the lagoon can function properly? And that means checking things, doing O&M, taking care of our blowers, looking at our berms, things along those lines. So what is BOD? So BOD is basically everything in the water that can be oxidized by bacteria. So that's all the food. And so if you look over here to the right, I just have a little diagram of BOD test procedure. Some of you might have labs at your facilities, others might not, so you might not be super familiar with this, but we take the sample. We're going to dilute that sample, so we're going to put a small amount of the sample into a BOD jar with dissolved with deionized water. We're going to take an initial dissolved oxygen measurement. We're going to then put that in an incubator for 5 days at 20 degrees Celsius, and then we're going to take a final dissolved oxygen measurement. And basically, we're going to then subtract the final from the initial, and then we'll see how many milligrams per liter of oxygen was consumed over that 5-day period of time. That's where that comes from in terms of milligrams per liter of BOD. A small twist on BOD, and some of your permits will actually say CBOD on them. So depending on your state, also depending on your watershed, you could have a BOD permit or you could have a CBOD permit. CBOD means that we have just carbonaceous biological oxygen demand. So really what we're trying to measure there is just the organic carbon. So it's a different kind of food. So we're trying not to measure any of the nitrogen or the nitrogenous oxygen demand when we do CBOD. The procedure for CBOD testing is exactly the same as what you see on that screen, except before we put it into the incubator, we actually add a little bit of nitrification inhibitor that makes sure that the nitrifying bugs can't actually convert ammonia into nitrate, because that would consume oxygen. So that's the big difference in that particular step, is that we're actually adding an inhibitor. So the next way we can break this down is we can actually look at soluble versus total. So for BOD, CBOD, and nitrogenous oxygen demand, we can look at it from a total, and we can look at it as a soluble. So the big difference here is that to get a soluble BOD reading, we would actually run it through a filter first. Most permits do not require a soluble BOD reading or a soluble CBOD reading, but it's really helpful when it comes to diagnosing problems. And a lot of times when your engineers are designing facilities, we use sort of these ratios where we make assumptions of how much is dissolved in when we look at a total CBOD reading to sort of make those designs. So we start to think, why is my effluent high in CBOD? So what could cause CBOD to go up? So the first thing we have to talk about is what's in your influent. So if your effluent's high, was your CBOD and your influent high? Because if your CBOD and your influent exceeds the actual design criteria of your facility, that your plant might not be able to actually treat that high of a CBOD. I like to tell stories. My favorite story regarding this is I was involved in a project over in Indiana. The facility was designed for 400 CBOD on the influent and 40 ammonia on the influent. And then we went out, we designed the plant. It worked, but it smelled really bad. And whenever we went back and we actually started taking samples, because the headworks had changed, the equalization tanks had changed, everything had changed, turns out the CBOD coming in the facility was actually over 1,000 milligrams per liter, and the ammonia was 40, but we're going to talk about something called total Kjeldahl nitrogen, which is includes the urea and organic nitrogen. That was over 140. And the reason was because the collection system was short. Now the operator wasn't doing anything wrong before. He had been reporting 400 CBOD, but basically the way the plant was set up, he wasn't able to sample properly. And so when the plant was designed, it was actually too small based on what the CBOD readings coming into the facility actually were. So we can also look at the TSS and the VSS, and we'll talk about what those are, but total suspended solids versus volatile suspended solids. And then what's happening between your lagoons? Most of us don't have one lagoon. Most of us have 2 lagoons, 3 lagoons, or 4 lagoons in series. I've seen systems that are 11 lagoons in size. So what's happening between those lagoons? That can be really important in terms of diagnosis, because maybe Lagoon 1 and 2 work really well, but maybe Lagoon 3 is filled with sludge and it's actually causing problems. So we need to sometimes look at sampling between lagoons. Sorry about that. So typically in most systems, the first lagoon will remove 80% of your CBOD. Now, that's a big generalization. In some systems it could be 70, in some systems it could be higher than 80. But when we look at that and we look at the original design, we want to make sure that in the future, periodically we test after our first lagoon to make sure that the first lagoon is actually doing what it's supposed to do. So that way we know what's going downstream is actually going to be at the proper concentrations where the downstream lagoons can actually treat that water. So between lagoons, a really good habit is to sometimes just take oxygen, take your DO between the lagoons. Maybe look at your pH between the lagoons. And if you see your DO coming out of the first lagoon might be too low or anaerobic, there are things that we need to look at. Maybe we can take a look at our blower and make sure our blower is working properly. It's amazing how sometimes valves might get accidentally bumped or closed. Maybe we're servicing something, we turn off a valve and we forget to open it back up when we're done servicing that. So maybe the lagoon's not getting the adequate amount of air. Look at our bubble patterns on our diffusers. Does it look like we're getting the same bubble pattern coming out of those diffusers? Maybe we have a torn membrane. Maybe we have fouled membranes. So these are things that we can look at. The other thing that sometimes happens if we don't have well-mixed ponds is we actually get the turnover. So when the temperature flips in the spring or fall, everything on the bottom comes to the top, and that can turn that pond anaerobic pretty quickly. You can usually tell that too because you'll see a massive amount of floating debris on top of the pond. So that one's usually pretty easy to diagnose. But we can look at that data and we can try to diagnose that. And then the other thing we can take a look at, that sometimes happens is, did we get a slug load of CBOD into the influent? So was there some sort of a strange event that led to a high degree of CBOD coming into the wastewater treatment plant that could have upset that first lagoon? A lot of times in lagoon systems, things that we have seen in the past that can cause this is things like industry, for example, food processing facilities that might be tied to the municipal sewer system. So a pig processing facility, pork facility, I've seen where they get large slug loads of fats, oils, and greases. Then that clogs up the headworks and that gets into the pond, and sometimes those fats, oils, and greases can actually foul the diffusers. There was one that I worked on in Southern Illinois where they had a slaughterhouse, and periodically the lagoon was bright red because of all of the blood that was being flushed from the slaughterhouse into the system. Now that does sort of get diluted over time, but that does cause upset because when you have BOD coming in at 2,000 or 3,000 milligrams per liter all at one time, that is going to cause an anaerobic environment, which can cause some upset to the facility, which then will trickle through your process because you'll be discharging higher CBOD down to the subsequent lagoons. And then last, what about a rain event? If all of a sudden we have a massive rain event and we have a collection system which is maybe old, and we just haven't had the cash to upkeep that, or we have a lot of people who have leaky laterals on their property that are coming into our sewer system, we could get a lot of water, and that could cause short circuiting in those lagoons because the flow becomes so fast that we could actually start shooting water straight through those lagoons and getting very, very, very short effective hydraulic retention times. So the next one that we like to look at that we can tie into BOD here in a little bit is our total solids, and we'll look at total suspended solids and volatile solids. And then we can also break that down further into dissolved solids. So like I said, some of you might not have labs. This diagram gets a little bit complicated, but typically what a lab will do is they'll take your sample. First thing they're gonna do is they're gonna filter those samples, and then they're gonna set that filter paper aside. They're gonna put it into a little thing of tin foil, and they're gonna put it into an evaporator, and then they're gonna dry that filter out. Then they'll use that, they'll know the weight of the filter, they know the weight of the little aluminum thing, a little aluminum cup that they have on there, and they can weigh that. And then that will determine the total suspended solids, because everything that's a particle will actually get trapped on top of that filter. Now, that particle could be dirt, sand, grit, it could be hair, fiber, bacteria, anything that comes in your influent. On the effluent side, that total suspended solids could be floating sludge, it could be inorganic particles, it could be the bacteria that was doing the treatment, or it could be algae or even duckweed. And you can imagine if you just get one little piece of duckweed on that filter, that weighs a lot compared to everything else that's in your water, so that can actually throw your results off quite a bit. Once they take that and they weigh it, they're going to put it into a furnace, and they're going to put it in a furnace about 400 degrees Celsius. That's going to cook all of the organic matter, and it's going to make it combust. Once they take it out, they can weigh it, and then if they compare the weight of what's left on the filter, that's going to be just the inorganic stuff, They subtract that from the original total solids, and that's going to tell them how much volatile solids was in there. So it's going to tell them how much bacteria, organic matter, algae, things along those lines were actually on that filter, and how much of it. And so then they can figure out how much is sand and inorganic and how much is volatile. That's a lot. Now, we can do the exact same thing for dissolved solids. So basically, they'll do the exact same test, but instead of taking the filter, they'll take all the liquid that passed through the filter, and they'll do all the same things again. Now, this is really important because by doing this and looking at dissolved solids versus suspended solids, we can determine, is there a lot of dissolved salts, for example, or is it suspended solids like algae or dirt or things along those lines. So it becomes very important down the road for diagnosing potential problems. So let's move on from this. So high TSS. So a lot of times when we're lagoon operators, one of the first things that we battle against for TSS is algae. And algae do a lot of treatment in lagoons. Whenever we have facultative lagoons, a large percentage of the oxygen is actually produced by the algae. You guys know this because if you take dissolved oxygen readings at 8 in the morning, you might have a 4 or 5. If you take them at 2 or 3 in the afternoon, you might have a dissolved oxygen of 7 or 8. You'll see your pHs change because of the algae, because as they do their job and they oxygenate the water, their pH will rise a lot of times. So you know that they're actually doing things in the water. And that's good until we get to our effluent. And in the effluent end, some lagoons will actually have too much algae. A lot of times that's because we've gotten the BOD really, really low, but we still have quite a bit of nutrient in the water, and the algae use those nutrients. They use the ammonia, they use the phosphorus, that's their food, they use carbon dioxide from the air. And so we've done a great job of removing the CBOD, but we have nutrients left over. Those nutrients then help the algae grow because it's basically like fertilizer, and those algae will show up as TSS in your effluent. These algae, this little guy here is a little guy named Volvox. They have lots of little tails that they can use to swim around. So they'll actually swim upwards toward the light so they can do photosynthesis and grow more. So sometimes whenever we're looking at this, one of the things that we need to do when we have high TSS, one of the first things we need to do is go back to that previous screen and try to figure out if that TSS is actually volatile solids, or is that TSS non-volatile solids? Is it inorganic solids? Because if it's volatile solids, and you can tell this too because the water might look a little green, that's probably because it's a lot of algae. If it's inorganic solids, then that means probably that we're getting some sludge that's kind of carrying through the system, and so it's broken down, but it's inorganic things like salts and things along those lines that are moving their way through the system and getting into the system and causing high TSS. So most TSS that comes into your plant will settle out in the first cell. That's where we want it to be. As we aerate those cells, it'll slowly digest over time. We don't want it to go anaerobic because that'll cause odors. But if we have floating sludge in the polishing lagoons, one of the things that we might want to look at is, do we have too much sludge in the lagoon? When you get excessive sludge and it builds up too thick, you start to get anaerobic layers in that sludge, and those bacteria will produce methane just like they would in an anaerobic digester. As those methane bubbles get caught on the sludge, they'll actually cause it to bubble up, and it'll cause it to float on the surface. Sometimes at the same time as the methane causing the bubbles, you might smell some rotten egg smell. That's hydrogen sulfide. That's a pretty dangerous gas. That's why we don't like to go in confined spaces, because at very low concentrations, it can cause you to pass out and it can actually kill you. That's also caused by anaerobic bacteria who are degrading sulfates. And so if we have a polishing pond that has these types of symptoms where we have a lot of floating sludge, we have these nasty odors on them, what that means is that we might need to remove sludge from the polishing pond, reduce that sludge blanket. In some cases, you can intermittently aerate that lagoon. So if you have a controlled discharge lagoon, you can aerate the final polishing cell when you're not discharging, and then you can turn those aerators way, way down or even off for short periods of time just to discharge. So those are some solutions to those nasty smells and floating sludges in your polishing ponds. If it's happening upstream in your facultative lagoons, you probably need to add more aeration to help dissolve those sludge blankets, or go ahead and dredge those ponds. But we all know dredging is very, very expensive. So lastly, I was at a lagoon down in Arkansas, and the lagoon was just green. It was very bright green. It was very, very pretty. But that was an indication that they had an algae bloom. That algae then was causing high TSS because as it went through the system, their polishing pond was pretty small, the velocity was staying pretty high, and then those algal cells were going out the back end of the system, especially when they had a rain event, because what would happen is all of the rain would come in and it would push all the algae through all at one time, and they'd get a big slug of TSS that would go out the back end. So what can we do for that? We can do some really simple things for that. You can add things like barley straw to the influent end of your lagoon. This has been used for decades. You can put the barley straw in there. The barley straw then can release a toxin. It's an algicide, and it doesn't kill algae blooms, but it does prevent the growth of new algae. So typically when people use barley straw, they'll put that in there in the early part of the season, usually February, before the algae starts to grow, before it gets too warm. That barley straw starts to decay. The bacteria actually eat the barley straw, releases those toxins, and helps prevent algae from growing. The other thing we can do is we can add lagoon covers in the last cell, in the polishing cells. Lagoon covers then can block the sunlight. By blocking the sunlight, that reduces the algae in the effluent. Those algae will die and they'll settle out in the polishing pond. In some cases, we've seen lagoon operators will use a little bit of chemical to help coagulate those algae and help them sink so they precipitate out in the polishing pond before they get to the effluent line. So now we're going to talk a little bit about that BOD to TSS ratio. So when you look at the BOD and TSS in your effluent, so TSS is the first number, BOD5 is the second number. And if you have very little TSS, or very high TSS and very little BOD, you have old sludge solubilization, so that sludge is dissolving. And so it's not showing up as TSS, but it's showing up as soluble BOD, and it's getting released back into the water columns as soluble BOD. And so that can actually cause you to violate your BOD permit while not violating your TSS permit, because you actually have sludge rotting in the system. You can check this, and you can actually look at some of the causes. So are you getting nitrification in your BOD test? So one of the things you want to look at right off the bat is, if you're taking a BOD test, is your BOD low enough in your BOD bottle that you're actually starting to see nitrification occur in your BOD test bottle? And that's actually what's causing your BOD to go up. So it could be a testing issue. First of all, because really what most of our permits say nowadays is our permits say CBOD, and this is sort of an interesting thing because I'm lazy too, and even though I know it's CBOD on most of my permits that I work on, I still say BOD because it's just kind of cumbersome to say CBOD. So that is one of the things that we can look at there from a testing perspective is are we doing the right test? Do we need to add a nitrification inhibitor to try to look at that? To give you an idea, if you have a BOD permit of say 35, you would probably, on a CBOD test, you'd probably end up with like a 25 or a 30 permit, maybe like 80% of the total value of that BOD. So just to give you an idea how that ratio works there. If it's equal, if your TSS and your BOD is the same, let's just say it's 30 milligrams per liter, that could be a sign that you're getting some short circuiting and you have some untreated effluent or untreated wastewater that's actually mixing into the effluent because it's moving through the system too fast. A normal, quote unquote normal, what we would expect to see would be something like a 1.5 to 1. So if you have say 30 TSS, we'd expect somewhere around 20 BOD. And that would be sort of normal. Your TSS typically will just be a little bit higher than your BOD, because some of that TSS will can contribute to the BOD, and some of it's going to be inorganic and not contribute to the BOD. Now, I'm going to warn you guys, sometimes these numbers, you know, don't necessarily work great because it kind of depends on your permit, right? So if you have ammonia limits, if you have BOD limits only, if you have a high BOD limit, so there is some play here. So these aren't, you know, hard and fast. These are just really good guidelines. I would use them as a rule of thumb. And then lastly, if you have a really high TSS, like say your lagoon's putting out 60 or 70 TSS, but your BOD ratio, your BOD is actually very, very low, that's usually going to be a sign of one or two things. Maybe a lot of algae overgrowth. So those particles are just going out, they're getting, you know, they're going out in your effluent and they're causing a lot of TSS, but they're not a lot of BOD. Me personally, as a biologist, you know, discharging algae into a stream isn't always that bad, because if there's no food for them in the stream, they're not going to take over the stream anyway. But we have to meet our permit, so we have to make sure that we try to take care of that. Like I said earlier too, if you have a duckweed bloom, you know, one or two little pieces of duckweed can really blow up your TSS reading, because they're very, very heavy compared to everything else in the water. The other thing that can happen with high TSS and low BOD is you might be getting a lot of inorganic sludge particles that are kind of re-releasing. So if you get some turnover, if you get some agitation in that pond, like if it's really, really windy and your polishing pond starts to mix that pond a lot, you could actually get some of that old sludge that gets brought back up into the water column, and it can actually cause some high TSS in your effluent. So again, I like this chart because it's a really great rule of thumb that kind of gets me pointed in the right direction to say, hey, do I need to go out and maybe take a soluble BOD reading to make sure it's actually soluble versus total BOD? Do I need it, you know? So it kind of gives me some ways to diagnose this. When we start to look at nutrients, and we get into the nutrient limits, these are all over the map in terms of the United States. So we see lagoons throughout the United States with no ammonia limits. We see lagoons with 1 ammonia limit on them. So, and everything in between. So this is becoming a real trick for lagoons to learn how to manage this, because some lagoons, this is really new. On top of that, we're starting to see lagoons that have total nitrogen limits. And total nitrogen basically is everything in the lagoon that contains nitrogen. So we're talking about ammonia, we're talking about organic nitrogen, so this would be urea, and we're talking about nitrates. And so nitrates, when you have a lagoon that's nitrifying, we're converting the ammonia into nitrates. So we might meet our ammonia limit of 1, but we might have 30 milligrams per liter of nitrates. We might need to get those down in order to meet a total nitrogen limit. We have TKN, total Kaldol nitrogen. In some states, we don't have ammonia limits. We have total Kaldol nitrogen limits, meaning that they want to look at ammonia and organic nitrogen. For example, that plant that I told you about earlier where it was really overloaded, they had 40 ammonia, but they had 140 total Kaldol nitrogen. Once that total Kaldol nitrogen or TKN gets into the wastewater treatment plant, that's going to break down and that's going to become ammonia. So in a lot of states now, when we design our wastewater treatment facilities, they want us to design off of TKN, not off of ammonia, to make sure that we can actually have the capacity inside of the wastewater lagoon to break down all the TKN into ammonia, so we don't undersupply oxygen to the system. And then some states have what they call TIN, which is your total inorganic nitrogen. So when we talk about total inorganic nitrogen, that is the sum of ammonia and your nitrates. So that leaves out the organic nitrogen part. So totally confusing, because there is no standard across the United States. Every state uses these 4 terms in their permits, and they'll use them in different fashions. And you'll have different permit limits from state to state. Then lastly, we have phosphorus. And phosphorus is a new one. Phosphorus is the nutrient that leaves the wastewater treatment plants that actually leads to algae blooms in the streams and lakes that we discharge into. And a lot of times the phosphorus is actually what's leading to the algae bloom inside of your lagoon. So some of the ways we can actually remove algae from the lagoon itself is to treat the phosphorus inside of your lagoon. and that can actually reduce your algae blooms and help with your TSS. So let's talk about these nutrients, what they mean and how we might diagnose these things. So whenever you have a lagoon, most of the nitrogen that enters the lagoons is in the form of ammonia or TKN. That TKN in this case would be urea. That usually comes from your pee. So it's ammonia or TKN. That ammonia and TKN would then get converted into nitrate by bacteria that are going to use oxygen. These guys use a lot of oxygen. They're using 4.6 pounds of oxygen for every pound of ammonia or TKN in the system. So a lot of times, if you have a permit that has a 1 ammonia, it's almost going to double the amount of oxygen you have to supply to your lagoon. So it's going to increase your power costs a lot, and it's going to increase the amount of oxygen you have to put into that lagoon. These bacteria grow very, very slowly. They are a real hassle. They're finicky little bacteria. They're kind of wimps. So there's a lot of factors that contribute to their growth. One of those factors is alkalinity. A lot of us don't measure alkalinity in our lagoon systems, but alkalinity is a way to measure the amount of carbon, inorganic carbon that's in the water. And the measurement's actually calcium carbonate when you look at your testing equipment. So every time you get rid of 1 pound of ammonia and turn it into nitrate, that removes 7.14 pounds of alkalinity from your system. So what ends up happening is as you start to remove the ammonia, the pH of your system actually starts to go down as you turn that ammonia into nitrate. The ammonia conversion does not progress well if you have high CBOD levels. So a lot of times you won't see very much, if any, nitrification occurring inside of your first cell of your lagoon. Usually your nitrification is really going to start to happen when your CBOD level gets below around 50. Then you're going to start to see the nitrification kick in. And then ammonia removal slows down significantly whenever it gets cold. 4 degrees Celsius, 39 degrees Fahrenheit is sort of the coldest your water will get in a lagoon and stay liquid. That's going to be on the bottom of your lagoon. You're going to be at about half the pace or slower at that particular temperature. You can nitrify all the way down to just above freezing, but it goes very, very, very slow. So this little chart down in the bottom is some of the things that we look at whenever we're not getting good nitrification. So say I've got a permit of 1 and I just can't ever seem to get below 5 ammonia on my wastewater. So I need to look at my dissolved oxygen. Am I at least 2 to 4 milligrams per liter for dissolved oxygen? Because if I'm not there, I'm not going to be able to nitrify. What's my alkalinity? My rule of thumb for alkalinity is take the amount of ammonia in your influent, multiply it by 7, and then add 100 milligrams per liter. That's usually my rule of thumb for what I need to do nitrification. Your pH. Your pH needs to be between 6.2 and 7.9. If it goes too low, if it goes below 6.2, you're not going to nitrify. Really, I don't like to see my pH anywhere below 6.5. What's your temperature? Warmer water tends to nitrify faster than colder water, just like anything. Toxins. If you have industrial clients, are they cleaning, for example? A lot of times when they clean between process runs or if they're changing over their lines, they'll clean their equipment with quaternary ammonias, quaternary amines. Do you have a campground connected to your system? Do you have gas stations that have RV dump centers? Because that blue water that's in those RVs that keeps their black water tanks from stinking in their RV is a good way to kill an entire wastewater treatment plant and stop nitrification from happening. So a lot of times when we see nitrification stop immediately, we'll do a test for quat ammonia, or we'll look at different types of chlorines or heavy metals or things like that that can be used as disinfectants. And then lastly, do you actually have bacteria in there that can do it? So do you actually have nitrifiers? Sometimes if you have a kill where you have a lot of toxins, sometimes we actually have to then put new nitrifiers in there. And believe it or not, there are companies that sell nitrifiers. We order them by the gallon. And sometimes we have to bring those out there and we have to pour them into the lagoon because we killed off our system due to toxins that have come in from one of our clients. So efficient nitrification and nutrient removal. So I alluded to this earlier. So one of the things you look at when you talk about ammonia removal is the energy cost. So ammonia removal via nitrification requires a good bit more O2 for aeration. So we're talking usually doubling our oxygen demand when we start to do nitrification. If you're to look at a BOD test, typically on an influent BOD test, if it's a 5-day BOD test, you're not going to pick up a lot of that nitrification. But if you go to a 10-day BOD test, you will see that full nitrification oxygen demand on a 10-day influent BOD test. But you can also just test that by testing the ammonia, and you can calculate it that way. So it's a lot easier way to do it. The interesting thing is there's different bugs than what it takes to break down BOD. So the BOD bugs are super fast. They're strong. They eat organic carbon just like me and you. They move really quickly. So they will always outcompete the autotrophs for space, for water, and for food. So that's why we need to get rid of all that BOD before we can get to that nitrification to occur, because they have to have space and water and food so they can do their job. Once the BOD is at a low level, then those autotrophs will start to nitrify, and they will start to convert that ammonia into nitrate. Providing excess oxygen only results in extra expense. So if I need 4.6 pounds of oxygen for every pound of ammonia, it does not do me any good to provide 10 pounds of oxygen per pound of ammonia. That's not going to help. That's not going to do anything for me. All it's going to do is double the cost of my aeration cost. So we need to try to target that 2 to 4 milligrams per liter of dissolved oxygen in order to really make sure that we can nitrify. But you can see that graph over here. You can see that if we're at 2 milligrams per liter of oxygen, maybe this blower cost per year is $5,000. But if I try to pump it up to 8, now I've quadrupled my blower aeration cost. That's a huge O&M budget. So if we can get that down, even if we can just, if we want to be safe and go to 4, we've still saved over $12,000 for that per year on that wastewater treatment facility. pH, so this is out of the EPA design guide, our operations guide. So you can see at 7.2, nitrifiers are super happy. 100% activity, you put them in, they do their job. But as the pH decreases, you can see at 7, just a 0.2 difference in pH, they lose 17% of their effectiveness. And if you get down to 6.2, they basically aren't doing anything. They're 83% reduction in activity. So they're really not doing what they need to be doing at that pH. So we need to make sure our pH is at an adequate level. So that's another thing we need to test inside of our lagoons. So to give you an idea about why your ammonia could be high, check your CBOD in the aerated lagoons. If your CBOD is too high, you can't nitrify. So sometimes the ammonia, you might not really have an ammonia problem. You might have a CBOD problem that's causing the ammonia problem. So we need to look at our aerators again, make sure our CBOD is getting to where it needs to be. Make sure we don't have foul diffusers, make sure our blowers are working right, make sure we don't have torn diffusers, make sure we haven't accidentally turned off a valve, things along those lines. Check your O2 level. Is it too low? Because if it's too low, you're not going to nitrify very well. Check our alkalinity and pH. This particular graph here I have, if you see this alkalinity line, that's the blue line, you can see that it went from 140 alkalinity down to around 50 alkalinity. On the alkalinity is on the left axis. And then you can see on the right axis, the corresponding ammonia level. The ammonia was about 30, and the ammonia actually dropped to about 3. So from going to 30 to 3, our alkalinity went from 140 to 50. So this plant really could not nitrify anymore because they just did not have enough alkalinity in the water. We actually did some experimentation here. We actually put some alkalinity in, and once we put the alkalinity into the water, they were actually able to nitrify all the way down to 1. Another thing is you need to take a look at your water temperature. If the water's under 4 degrees Celsius, the nitrification is going to be really slow. There's not a lot we can do about that. Depending on where we're at in the United States, we can hybridize lagoons, we can do some things along those lines, we can implement some other strategies, but when you're at 4 degrees Celsius, nitrification is just going to be very, very slow. So we have to be creative on how to do that. Carbonate alkalinity, take you back to some high school chemistry classes maybe. So when your pH is under 6.2, most of the carbon that's in your water is carbonic acid. So obviously acid is not an environment that most living organisms like to live in. So we have carbonic acid in the water at that point, or carbon dioxide gas. It kind of goes back and forth between carbonic and carbon dioxide gas, finds another equilibrium. Between the 6.2 and roughly 11, at that point, our most of our carbon is in the form of bicarbonate. That's just baking soda, guys. That's just nothing but baking soda. That's Arm & Hammer. And so Arm & Hammer is great when it's in the water because it really resists pH change. It really can pick up protons and it can pick up hydroxyls and it can really try to maintain that pH just in that perfect range. But then as the carbon gets consumed, we can start to push it down to be more acidic, and that's what happens when we do nitrification. And then the carbonate, that's your limestone. Calcium carbonate is actually the unit that we measure alkalinity in. So whenever you see, say it's 200 milligrams per liter of calcium carbonate, that's one way. Some people actually would then write down, oh, nope, that's 400 milligrams per liter of bicarbonate. So that's another way. And some states actually have a different way of monitoring it that they call milliequivalents, but we're not going to get into that. So your alkalinity and nitrification, nitrifying bacteria are autotrophs. So again, they use that inorganic carbon. They want to eat that baking soda. They gain carbon from the carbonates in the water. The nitrification takes out 7.1 milligrams per liter of that alkalinity, which is the way we measure that carbonate in the water. So for every 1 milligram, that's for every 1 milligram of ammonia removed. So the rule of thumb, just to be safe, let's just call it 8 milligrams per liter of alkalinity for every 1 milligram per liter of alkalinity. If we use an 8-to-1 ratio, we've got a little bit of an up buffer, and we probably won't go wrong. Residual alkalinity, this is sort of a personal preference. Really, you need between 50 and 80 milligrams per liter as your endpoint. I usually use about 100 milligrams per liter as my target. So again, here's just a little graph. Nitrous ammonius and nitrobacter. The nitrous ammonius are the bacteria that actually take ammonia and convert it into nitrate. The nitrobacters are the ones that actually take the nitrite and convert it into nitrate. So it's a two-step process. But you can see on both of these, when the pH is below 6.5, there's very little activity to zero activity. When the pH gets over 7.8, you really start to see the activity drop again. So you need to keep that pH in that nice sweet spot somewhere around 7.2 to 7.5. Looks like I need to speed up here. I'm running out of time. So here's what I was just talking about a little bit ago. Calculating your alkalinity requirement. You can use an 8-to-1 ratio, and that should give you a pretty good ratio. You can also do it by the 7.14 and add 100, which is what I typically like to do. When we look at this, how can you get it? You can buy it as a powder. It's the easiest. It's just baking soda, cheap. You can get lime, you can get soda ash, or you can get caustic soda or magnesium hydroxide, which is the highest price. The problem with soda ash and lime and caustic soda also is that they can be a little bit hard to handle. They're hazardous materials. You can actually get chemical burns because they are so basic. So, but it's bulky, and they all have their own pros and cons in terms of the amount you have to use, the price, and the different effects you can have. So chemical addition, you can actually do this continuously based on just estimates, or you can use pH control where you can dose on pH. So if your pH goes down, it'll actually start to dose these chemicals into the water. Once the pH comes up too high, it'll turn off the dosing and you won't dose anymore. So total nitrogen removal. This is the denitrification process. So this is really accomplished by converting nitrate into nitrogen gas. So this requires a low oxygen environment. 4.5 to 5 pounds of CBOD are typically used per pound of nitrate to do this. So again, these are heterotrophs, same as your guys that like to use oxygen. But if we take the oxygen away from those heterotrophs, they'll actually start to use nitrate as their oxygen source. And one really nice thing too is that denitrification actually starts to recharge the alkalinity, and it'll add some of that alkalinity back into the water. So if we need to do nitrification, we can actually get a recharge here and reduce any potential chemical dosage that we want to try to avoid at all costs, because chemicals are just expensive and complicated to dose in many cases. So how do you denitrify? So if we denitrify and we've already removed all the BOD at the beginning of the process, we have all this nitrate at the end of the process, how do we get the nitrate that we need to denitrify in contact with the CBOD that we need to consume to do that denitrification? And there's a couple different ways. One of the things we can do is we can recycle that nitrate back to the front of the plant. So if we bring that nitrate all the way back to the front of the plant, we can actually denitrify at the beginning of the plant, break down that BOD, put more alkalinity into the water, which is then going to reduce our need for aeration because we're breaking down BOD anaerobically. We're putting bicarbonate back into the water, which is going to help our nitrification. So it has some really good benefits. And it's easy because there's no chemical dosage. If our permit is between, say, 8 and 10 total nitrogen, recycling works really well. So to get that good TN removal, we first have to get the nitrification down to about 1. Then we need to get that nitrate back into a mixture with that CBOD by recycling it. In lagoons, typically a recycle rate of 1 to 2 times your flow is really going to suffice. So if you're getting 100,000 gallons a day, recycling 100,000 to 200,000 gallons a day is usually going to be sufficient to do that nitrification. If you can't recycle for some reason, or if you have an incredibly stringent permit, say below 7 milligrams per liter, you can then put on a supplemental system at the end where you would add BOD back into the system at the end to raise the BOD, create an anaerobic zone at the end of the system. So the nitrate then makes it an anoxic zone, so you can denitrify after the system. And you can do both of these things together. So you can actually recycle, do pre-anoxic removal of total nitrogen, and then you could do a post total nitrogen system with a little bit of chemical dosage to meet a really strict permit. So what do we do to diagnose these things? So ammonia alone doesn't tell the whole story. We need to compare our ammonia to our nitrate. So maybe my total nitrogen's high, but is my ammonia also high? To get a good total nitrogen removal, we have to get our ammonia down usually to 1 or 2 milligrams per liter. So ammonia needs to be low. We need to look at the nitrate, add that in together, and we need to compare those results in a matrix. We also need to look at our temperature, our dissolved oxygen, our mixing, our hydraulics, so are we short circuiting? And we need to look at those operational issues there, and we need to resample to verify to make sure that we've had an improvement. So again, this little matrix we've put together here, so low ammonia, low nitrate, effective nitrogen removal, you've been assimilating that, you've been converting that to nitrate. High nitrate, ammonia converted to nitrate, denitrification is limited, so we're not denitrifying here. And so we could reduce our oxygen to create an anoxic zone, add some carbon, and we could do the denitrification. If we have high ammonia, and nitrification is limited, maybe we have cold temperatures, maybe we have low DO, maybe we have bad mixing, maybe we have short circuiting. So in this case, we would increase our aeration, look at our mixing, verify our hydraulic retention time, make sure we're not short circuiting, and then look at our loading and make sure our loading's coming in. Unstable partial conversion, maybe incomplete or fluctuating nitrification. Sometimes we get stuck at nitrite. Changing loads and temperatures, maybe we just have an unstable influent. And these things can cause these particular issues. One thing I'm just going to interject here real quick, because some of you might have to drop off right at an hour, is that this is why it's really important to take influent data all the time, even if our permit does not require us to take influent data. It's really critical to go ahead and take that influent data regardless, because that way when a problem arises, you have the data in front of you to go ahead and start diagnosing problems. So you have to define that problem, identify what's changing in my BOD, TSS, ammonia. Is that changing in the effluent? What's going on in my influent? What's going on cell to cell? Should I periodically be testing DO and pH and things like that, BOD between cells? Absolutely. It's good to just spot check it. So if you're testing weekly for everything else, maybe once a month, do things in between cells just to make sure things are going well. Look at the cause. So look at those ratios. Look at the TSS to BOD ratio. Look at our nitrification and ammonia parameters, our little matrix there. And you can start to figure out what biological problems might be occurring, what hydraulic issues might be going on, what kind of solids related issues like turnover, algae, or duckweed might be happening. Check the Lagoon fundamentals. Look at our results. Look at the DO, the temperature, the mixing, our pHs. Look at our nutrients in those cells and try to figure out which one of those factors is limiting. Maybe everything looks great, but if my temperature is 1 degree Celsius, I'm not probably going to nitrify very well. I'm going to have to come up with a really creative solution. Look at our operational responses. So do we need to look at aeration? Do we need to do maintenance on a blower? Do we need to fix a diffuser? Do we need to look at short circuiting? So should I add a baffle to my system to make sure I don't short circuit? Do I need to add aeration in my cell to make sure I don't short circuit just by mixing the water? How can I manage algae and duckweed? Do I need to put a floating cover on the last cell to make sure I don't have algae and duckweed in my last cell? Modify the loading. Do I need an excess flow basin? Do I need an equalization basin? What should I be doing here to get that flow going into the system in a proper way? And then look at my monitoring practices. When am I sampling? How often am I sampling? Grab samples when maybe a composite sample is more appropriate or vice versa. And then verify and refine. So resample these after we make changes, confirm that there's a response in the data, document what you've been doing. You have to take notes every time we make these operational changes. And I know we take calls all the time from operators, helping them diagnose these issues. So we work with a lot of our clients to actually help them diagnose this and come up with solutions. So this is a little chart I made. Basically, when you have your CBOD here and your ammonia coming in, you have this anoxic zone. Aeration is going to get rid of the BOD. Aeration is going to convert that ammonia into nitrate. We're going to have a settling zone. We have a recycle line where we take that nitrate all the way back around to the head of the plant, mix it with the CBOD up here in the front so we can do the denitrification up here in the front. If all of this is working well, we have all of our recycle rates going well, we have all of our aeration or mixing. You can see here we have baffles to limit short circuiting in those two cells. We should be able to put out a really good low total nitrogen and low BOD water, a really good effluent, and meet all of these permits with lagoons. So first of all, we need to just understand your permit, look at your performance, look at those major factors like loading, design, hydraulics, and biomass health. You have to look at your must-knows. You have to understand your lagoon, look at the loadings, your design loadings versus your actual loadings, your HRT, your DOs, your pHs, your temperatures. Are you getting dumped on? Are you getting some kind of contaminant? What are your algae levels? How are those affecting your TSS? Proper sampling. I'm a stickler on this. Proper sampling does not mean just do what your permit says. I'm a huge believer in taking influent samples all the time. Whenever you take an effluent sample, take an influent sample. That way, whenever you have a problem, you have the data already in front of you to make those design or operational decisions. Record keeping, doesn't matter how well we take samples if we're not keeping those records, if we're not putting them into a notebook, if we're not putting them into a spreadsheet where we can actually keep track of them and share those, because maybe I only operate 3 days a week and there's another operator the other 3 days of the week. We need to make sure that we can share that data and record keep so we can troubleshoot our operations. All right, so I apologize for running a little bit long, but are there any questions?
Hey, Daniel, I've got one question. Anyone else that wants to submit a question will answer after the webinar's concluded.
Okay.
So just to confirm, the TSS and BOD5 ratios that you presented are just guidelines and not hard and fast rules.
Right, so they are guidelines because it's also going to depend upon your permit and how your permits, so if you have really low BOD and TSS ratios, those might vary just a little bit on those effluent. So yeah, they are a very good guideline and they're a good place to get you started.
That's it for questions. Certificates of attendance will go out in about an hour. If you need to have a certificate with time, please let me know. Email eve@lagoons.com.
Thank you, everybody.